Hello and welcome to another differential equations video. We're looking at an overview for Module 8, where we get into the series solutions techniques for differential equations. And so you should have seen series covered in Calculus 2, but it may have been a while and you may have never really gotten it. And I think one of the issues with that is the sigma notation. So one thing I recommend is with all these problems to expand the sigma notation and write it out in the expanded form to about 4 or 5 terms, and then put the ellipses to better understand the sigma notation. If you do this enough, then you'll start to, I think, read the sigma notation as it's intended. And the basis behind our method is that the solution to a differential equation y can be modeled by the power series, the infinite polynomial sum from n equals 0 to infinity of a sub n x to the n. And so when we write this out in the expanded form, we start with whatever the starting index is, and that's the first term, and then just evaluate the nth term expression to the right of sigma with that n value. So a sub 0, x to the 0. And then simplify. X to the 0 is 1, and so it's just a sub 0. And then we just increase that index by 1 and keep going up until we hit to the top value, or keep going if that's infinity. So when n equals 1, that's our next one, we get a sub 1 x, a sub 1 x to the 1. And x to the 1 is x, so we get a1x. And so on for n equals 2 and n equals 3. So this will be our solution, and really our goal is to figure out what those a's are. And so it feels a little bit like an undetermined coefficients problem. But ultimately we'll develop a recursive formula that is ideal for computationally generating as many of these a's as we want. But first we're going to need to take some derivatives of this power series. I guess before that, you also want to be able to go from the expanded form back to the sigma notation. So take a second and see if you can identify which sigma notation goes along with the expanded form at the top for that series. All right, and if you saw a mistake there, that's because there is one. This should be a 2, right? All right, in that case, then maybe identify that D was the correct answer. That this is really a 2 times a 1 times an a2 times an x to the 0, which is the n equals 0 version of that. And this is a 3 times a 2 times a3x to the 1, and n equals 1. And then a 4 times a 3 times a4x squared, which is when n equals 2. So the correct answer is D, though I have a typo to fix there in the slides. All right, so the power series is going to get put in a differential equation, which means we need to differentiate it. And again, I think it's easier to look at the expanded form first, and then differentiate it term by term, right? It's just a polynomial, so you can differentiate term by term just using the power rule. Derivative of a constant is 0. Derivative of a number times x is that number. And then for these other ones, we're going to bring the exponent out front and then decrease the exponent by 1. So we get the derivative there. And we see another typo. That should be y prime. As well. First time using these slides, as you can tell. All right, so going back um, from the expanded form to here, we can see that we don't really need to start at zero because the zeroth term is zero. So we can start at n equals one, and then we are going to be multiplying a by whatever its subscript is, 1a1, 2a2, 3a3, so n. And then you'll notice that the exponent on x is always one less than that, so x to the n minus 1. Now you also want to eventually be able to apply the derivative directly to the nth term expression. So looking at this, x is the variable, and so the power rule would say bring the n out front, and then decrease that exponent by 1, and then an is just a constant, so it just gets brought down. And it wouldn't be wrong to have a 0 here because when n equals 0, it would just include the 0th term. So you can take the derivative directly to the sigma notation there. All right, let's do one more derivative. So this is a second derivative, and we get a 0 for the second term now. Third term goes to a constant, 2a2, and then we need the power rule in this last one. 2 times 3 is 6a3x. So here we get kind of a 1 times 2, 2 times 3, 3 times 4, just like we had in the previous slide. And that kind of n times n minus 1 pattern comes up a lot with these series because of repeated use of the power rule. Also, since n equals 0 and n equals 1 are both 0, we can start at 2. And again, if you just think of directly differentiating this, you would take the exponent and you would multiply it out front, and then you would decrease the exponent by 1, and that's all that would change, right? So this form for the power series is always the case if our initial conditions are at 0 and we're using sort of a Maclaurin series centered at 0. We're going to have an example of when it's not centered at 0 and how you would handle that, but we'll focus on that case. And so these forms of y and its derivatives are kind of always the same. But rather than memorize them, I would say just know the original form of the solution and then differentiate it each time as you solve the problems. All right, so two other things that are kind of tricky and involve manipulating these summations are going to be covered now. And so one of those is that we're going to want to change the exponent on x, usually change it to x to the n. So that's what we'll look at here. And we'll look at doing it directly to the sigma notation, and then explaining that by taking the expanded form. So first you got to think like, what is the actual change to the exponent? I want to go from n minus 2 to n, and so what I'm really doing is I'm adding 2 to the exponent. Identifying that change is important because you'll mirror that same change with all the n's on the nth term expression. These are all plus 2's, right? So plus 2 to that subscript, plus 2 to the n minus 1, plus 2 to the n. And then to balance that out, we actually do the opposite to the starting index. In that case, the opposite of adding 2 is subtracting 2. Now, let's do the expanded form and then try to make sense of this. So for the expanded form here, I start when n equals 2, and so I have 2 times 2 minus 1 times a2 times x to the 2 minus 2, or x to the 0. So that's the n equals 2 term. And then n equals 3, I'm going to have 3 times 2, excuse me, times, sorry, times a sub 3, right? Just replacing all these n's with 3, times x to the 3 minus 2, or x to the 1. All right, one more. When n equals 4, I'm going to have 4 times 4 minus 1 times a4 times x to the 4 minus 2. All right, and so we want this series doesn't change. We're just changing the representation of it. And remember, I want it to be so that n equals 0. Or sorry, I want it to be so that it's x to the n. And so I want n to be these values, right? If it's going to be x to the n, then those are the n values. And so that makes it go n equals 0, n equals 1, n equals 2. But then you'll also see that for the other numbers to match up, they have to increase by 2, right? So for it to be a2, when n equals 0, it needs to be a n plus 2. And same with the 2 and the 1. So the expanded form is helpful here just for kind of agreeing with or understanding what's happening. But in general, you are choosing the change based on the exponent. You want to go from some exponent to another exponent. You identify what that change is, an addition or subtraction by some amount. You mirror that same, or maybe not mirrors, you do that exact same change consistently throughout the nth term expression in the sum, and then you do the opposite change on the starting index. All right, so why don't you give that a try with this summation and change it so that it's a summation that's equivalent where it's x to the n for that last factor. All right, pause it if you need some more time, but remember we would start by just seeing what this change is going to be. So changing this to x to the n, I'm actually decreasing that exponent by 1. That's a minus 1 there, right? So I need to do minus 1 to each of the other n's. So that's going to be a n minus 1, and then the 3 doesn't change, and then the n becomes an n minus 1 in parentheses. Right? So these are all minus 1s. Now for the starting index, that's the opposite, and so that would be opposite of subtracting 1 is adding 1. So adding 1 to 1 gives you 2. So that goes up by 1. So it's the corresponding summation where we have x to the n. All right, so once we get these with x to the n, we're going to want them to all start at the same starting index. And often that is they start at 1 or 2 or something like that, and we want them to start at 0. So you might think that's not possible because if we change the starting index, it changes the exponent. There's two ways this could work. And so one is that sometimes they are equivalent to the exact same summation starting at 1 or 0, and other times they're not. So let's just explore that here. And again, we're going to do it by first expanding. So just look at this first summation here. And we start when n equals 2, and so it would be 3. Oh, wait, no. Sorry. So let's let's see if we can change it to start at 0 and not change anything else. So all I've done is change the starting index. And then you might ask, well, are those equal? So now we look at the expanded forms and confirm. All right, so from the original summation, we would start at n equals 2, and we would have 3 times 2 times 1, a2 x squared. And then do n equals 3, 3 times 3 times 2, a3 x cubed. And we'll do one more, 3 times 4 times 3, a4 x to the fourth. And then we're going to look at the bottom sum. So for the bottom sum, the terms are the same, but we start when n equals 0. And so I should have given myself a little room here. Because remember, this is n equals 2, n equals 3, and n equals 4. And those will still be the 2, 3, and 4 terms. But this one is going to add on the n equals 0 term. But when n equals 0, you get 3 times 0 times negative 1, a0. And so it's actually 0 when n equals 0. Right? Because of that n right there. And then when n equals 1, it's also 0. And that's because of the n minus 1. It'd be 3 times 1 times 1 minus 1, which is 0. So when you have a factor of n, it will make the n equals 0 term 0. And when you have a factor of n minus 1, it will make the n equals 1 term 0. And since those two terms are 0, then these are, in fact, equal summations. So this is a case where we can just change the starting index from 2 to 0 and not change anything else. Pretty cool. But that doesn't always work. So that's something you want to check for, and you can check by looking for those factors. And so here we are able to make that change. Let's take a look at this next one. And this one also starts at n equals 2. And it would be 2 minus 1, which is 1, a 2 minus 1, a1, x squared. And then when n equals 3, be 3 minus 1, which is 2, a2, x cubed. And last one, when n equals 4, it would be 3, a3, x to the fourth. All right, but what about when n equals 0 and n equals 1? So when n equals 1, we do still have that n minus 1 factor, and so it would be 0, a0, x to the 1. However, when n equals 0, I actually get something that doesn't quite make sense. I get negative 1 times a to the negative 1 times x0. And remember, our a's start with a subscript of 0 and increase, so they only have the subscripts of whole numbers. So a sub negative 1 is not defined. So we actually can't do this because that doesn't make sense. So we can still make this thing start at 1, though. Because of that n minus 1, we can drop it from starting at 2 to starting at 1. So sometimes you can just make it start at 1 instead of 0. All right, last one. Try the same thing here. And at this point, maybe we can just look at the n equals 0 and n equals 2 term, or sorry, n equals 0 and n equals 1 terms, because all we're doing is adding those on to the beginning. And so when n equals 0, we actually get a 2a1 x to the 0. And when n equals 1, I get a 2a2x1. So these are actually not equivalent sums because we have some non-zero terms when n equals 0 and when n equals 1. So we're not able to just change that starting index to 0 or to 1. The trick doesn't work at all. So you're looking for those additional terms when n equals 0 or n equals 1 to be 0. If they're not 0, you can't just change it. So this one's stuck at 2, and that will happen. Those are kind of the three cases there. All right, how about this one? Can we start this one at n equals 0? All right, and the answer is yes, because we've got an an n factor there. So when n equals 0, you get 3 times 0 times a0 x to the 1, and that's 0. So it's exactly equivalent to the sum that starts at 0 with the same expression in it. So that one can be started at 0. But notice it wasn't 2 at the beginning. Sometimes they're at 1 and you want to drop it back to 0. All right, last thing we want to do is to change the ones that start at 0 to start at 1 or 2. And again, sometimes they're equivalent, sometimes they're not. We can always do this, but it sometimes involves taking some terms out. And so what we do is we just expand the sum. So let's just look at this one on the left here first. And when n equals 0, I get 2 times 1 times a2 times x to the 0. And when n equals 1, I get 3 times 2 a3x to the 1. And when n equals 2, I get 4 times 3 a4x squared. Right? So what I can do is I can have this 2a2 plus 6 a3x, and then all the rest of the terms are the sum from 2 to infinity of the exact same sum. So I've just kind of extracted the first two terms from the sigma notation and written them out front as individual terms. So those are all equivalent. Maybe I just want to take out the first one, then I would start my sum at 1 because it would include the n equals 1 term. You notice that the expression in the sigma notation is not changing. So those are all equivalent. All right, let's try it with the other example. Again, we'll expand it. So when n equals 0, I get 3 times -1 a -1 x to the 0. Okay, I think this is a typo. We saw this before. I can't have that one start at 0. So that was just a mistake. Should say 1 there. So we'll start when n equals 1. 3 times 0 times a0 x to the 1. And then when n equals 2, it's 3 times 1 a1 x squared. So in this case, the n equals 1 term is just 0. So again, sometimes you can change the starting index and it doesn't change anything. We saw it going from 2 to 1 or 1 to 0. or 2 to 0. But it can also go the other way. We don't usually need to make them start later than 2, but you could, if you want to just pull out that n equals 2 term, what is it, was 3a1x squared, then you can make it start at 3. So I think playing around with these things gives you a better feel for how they work. All right, so last thing here is to try this out. This summation starts at 1. See if you can make it start at 2. So just start with n equals 1, and you get 4 times 1 times a0 x to the 1. And then when n equals 2, 4 times 2 a1 x squared. And then when n equals 3, 4 times 3 a square, a sub 2 x cubed. And this 4a0x is all you need to pull out because the sum from n equals 2 to infinity is all the rest of the terms. So we're able to change that one to start at n equals 2 by just pulling out the n equals 1 term. Right. So that'll do it for this presentation, which contains images and text from Elementary Differential Equations of Boundary Value Problems by William Trench, CC by NCSA. Thank you so much. We'll see you in the next video.